This lab video is on processing and microstructure of cartridge brass, presented by Jake, Melby, and Zach of the Tuesday group of MSE 421 by Professor Anwar at Arizona State University. The objectives of this lab were twofold. The first objective was to identify the mechanical properties and how they change as the material relates to cold working and annealing. Cold working and annealing give almost the opposite effects on a material, so we wanted to identify the mechanical properties and how they changed. The second objective of this lab concerns microstructure and processing. We want to be able to observe the microstructure during different points in processing and be able to identify the material at different points of grinding, polishing, etching, and finally getting to a metallograph that we can identify different microstructures by visual inspection. Before we discuss what we actually did in this lab, it's vital to review some important concepts and theories. To fully understand what occurred in this lab, you must first understand cold working, annealing, metallurgical twinning, and a few processing steps such as mounting, grinding, polishing, and etching. Cold working is the mechanical plastic deformation of a material. There are several ways to do this, such as squeezing, bending, drawing, and shearing. This deformation can take place at any temperature below the recrystallization temperature, but is typically done at room temperature. When the metal is being deformed, it increases the dislocation density within the material, so the strength of the material increases and the ductility decreases. Annealing is a technique that can be used to undo some of the effects of cold working. It involves heating the sample up, keeping it at that temperature for a certain amount of time, and then letting it slowly cool. There are 3 steps in the annealing process: recovery, recrystallization, and grain growth. During the recovery phase, dislocations within the material rearrange through a method known as dislocation climb. While this is taking place, the grains are moving to a lower energy orientation with low angle grain boundaries. Once these low angle boundaries are formed, recrystallization begins. Atoms and dislocations continue to move. As they move, they create entire grains which are stress-free and without dislocations. These new grains have low internal energy, so it is favorable for them to be formed. Then, during the grain growth phase, atoms can jump in between the grains. The smaller grains disappear as the atoms jump from the smaller grains to the larger grains. This increases the average size of the grains and decreases the amount of grain boundaries. Overall, annealing decreases the strength and hardness of the material but increases the ductility. When observing a metallograph, something called twinning may be observed. There are 2 types of twins: mechanical and annealing. Mechanical twins occur when the sample is sheared significantly. This force dislocates numerous atoms simultaneously, which all shift within the material. Since this is a dislocation and creates an area of non-uniform structure, it increases the strength of the material. This type of dislocation can be found in BCC and HCP metals. Annealing twins can occur during the recrystallization phase of annealing. To achieve a more favorable orientation, a stacking fault can occur within the grain. This stacking fault can be seen in the metallograph and looks like a set of parallel lines. This type of twinning can occur in FCC metals. There are a few important things to know about the processing steps which take place in this experiment. These relate to the mounting, grinding, polishing, and etching of the metal sample. The main purpose of mounting the sample is to make it easier to handle. It is mounted in a substance which starts as a solution of liquid and quick-setting powder. When this solution is pressurized, the solution solidifies and can be easily carried and moved around. One side of the mount should have the metal exposed on the surface, which allows it to be easily ground, polished, and etched. The purpose of these steps is to remove marks on the metal, level the sample, and clean the surface. Grinding is done by rubbing the metal along many different roughnesses of paper-like materials. As it rubs against the material, parts of the metal are being taken away. The rougher the material is, the more it will take away. However, once the material is uniform, a less rough paper will be used. This paper is rubbed perpendicular in the direction of the first one so that it takes away the marks from the first grind. This process will continue through several different roughnesses and then it will be polished. Polishing is complete in a similar fashion to grinding, but uses a lubricant and a cloth instead of a rough paper. After it's polished, the metal sample has a mirror-like finish, which demonstrates how uniform the surface of the metal is. Etching is the final step of processing. It uses a solution of distilled water, ammonium hydroxide, and hydrogen peroxide to react on the surface of the metal sample. It reacts with the entire surface of the metal, but it reacts at different rates and reveals different things. For example, it etches at the grain boundaries relatively quickly, so it is very easy to see those. It reacts at twins and phase differences slower, so it must be etched for a longer amount of time to reveal them. When the etch is complete, a microscope should be able to reveal grain boundaries and grains, annealing twins, dirt and debris on the sample, scratches, and etch pits. Melby is going to describe to you how to do an experiment that would be similar to this.
The procedure is as follows. Cut the sample of cartridge brass into desired sample sizes. Anneal the specimen for 30 minutes at varying temperatures ranging from 100 degrees Celsius to 800 degrees Celsius, and an addition of 1 at room temperature. Using a phase diagram of cartridge brass, estimate the recrystallization temperature, measure the HRF, and plot the values. The recrystallization temperature can be determined from this plot. Compare the plot from slide 4 using the data from the previous lab. Anneal the sample for 10, 20, 30, 40, 60, and 5 minutes and determine the recrystallization temperature. Measure the hardness and plot the data. Resin mount the sample and carry out grinding, polishing, and etching of the sample. Using an optical microscope, observe the microstructure. Save the samples after observation. Sample mounting. Spray the PTFE mold release located on the inside of the reusable mold. Center the sample inside the mold, making sure the sample is placed face down. In proper proportions, mix the quick setting powder and liquid. Pour the contents into the mold, covering the sample less than half an inch. Place the mold into a pressure chamber under 2 bar pressure for 6 minutes. Precautions for the grinding and polishing procedure includes thoroughly cleaning the sample after each step, making sure your hands are clean throughout the whole process, viewing the microstructure under a microscope after each step of grinding and polishing, and rotating the sample 90 degrees after each grinding step to remove previous scratches. Grinding and polishing. Using the 320 grit, grind the sample until it is flat and scratches are uniform. Using the 600 grit, follow the procedure in step 1 and grind the sample for 2 to 3 minutes. Using the 1200 grit, follow the procedure in step 1 and grind the sample for 2 to 4 minutes. Step 3 can be substituted with a 6 micrometer diamond compound on white label polishing cloth and green lube. Using the 1 micrometer polishing paper, polish the sample for 2 minutes using generous amounts of green lube. Using the P cloth with silica, polish the sample for an additional 1 to 2 minutes. Etching of copper, brass, and bronze. Use fresh solutions for each etch and use the following time specifications. Using the following items, etch the sample to show the grains. For color metallography, use the following materials necessary to make the solution. Tint etched color metallography. Begin by etching to view the grains. Prepare a lead sulfate stock solution consisting of the following. Add 20 to 25 grams of cadmium chloride. Add 30 grams of citric acid. Mix each of these items above in the given order. Be sure to age the solutions in a dark bottle in darkness 24 hours prior to the experiment. To use the cadmium sulfide reagent, filter the excess precipitate from about 100 milliliter of the solution. The reagent will color the microstructure of ions and seals ranging from 20 to 90 seconds.
After all of that, you're finally ready to investigate your material. Take your sample and use an optical microscope to get a metallograph. If possible, use an optical microscope with a polarizer to be able to identify different important areas on your metallograph. Thank you for watching our lab video, and we hope you enjoyed it.